Also, the group 1A output from the spinal might change depending on whether further motor drives are changed, which also gives the output of the position or the reflexive of the muscles to the spinal cord. The influence of the dynamic creep is limited. What we mean by dynamic creep here is the creep that happens during cyclic loading, like during when you're running in a marathon. And a study was carried out that they found out that during running for long distances, the cyclic load effect or the dynamic creep effect is limited because of these following reasons. The slow nature of the dynamic creep phenomena, the small size of length changes of the tendon over time compared with the length changes of the tendon within a cycle. And on the other hand, when the dynamic creep happens, we'll find that the dynamic creep increases in small amounts, but the stiffness doesn't change. So this means that the dynamic creep isn't a damaging creep because the stiffness of the tendon remains constant, even with the increase in the dynamic creep. How they measure the forces of the tendons, because the way that they generate these curves, it's hard to use the human tendons or ligaments. So how they use it is they get tendons from animals or ligaments from animals, like for example pigs, and they test it. And then they apply to it the forces or the cyclic forces that may be applied to the tendons or the Achilles tendon while a person is running a marathon or something. So this is how they measure the force that they use to apply to the tendons or the ligaments of the animals. They use a buccal force transducer. As you can see here, the patient or the runner wears this transducer around his ankle. And here where it lies the Achilles tendon, so the forces can be measured and determined over the whole cycle. Stress relaxation. The second behavior of the tendon is stress relaxation. What we mean by stress relaxation is if constant deformation happens to the tendon will, the stress in the tendon itself will relax, and this also helps the tendon to dissipate the energy. So as the constant deformation, as we see the deformation here is constant, however, the stress or the load inside the tendon itself starts to decrease, even with the increase in deformation. Another way that the tendon overcomes this or that applies stresses is the areas where the strain is applied, they decrease the amount of water inside the tendon. This makes the tendon less viscous. When the tendon becomes less viscous, it becomes more elastic. So when it becomes more elastic, it can withstand more tensile stress without failure. The way they measure stress relaxation is by using the polarized light microscopy image analysis, where they found that there was a negative correlation between the brightness and relaxation modulus. The third property is hysteresis, or energy dissipation. When the tendons or ligaments, the stress strain diagram was measured for them, they found that the behavior of the tendon or ligament during the loading cycle differs from the unloading cycle. Here we see the loading cycle, the first loading cycle. But when you remove the strain, the stress, it takes this behavior. So there is a difference. There is a loss of energy. And this is what we mean by hysteresis or energy dissipation. The ligament or the tendon loses energy. And the way that they measure the hysteresis or energy dissipation is by comparison the amount of energy inside the loop compared to the area under the curve of the loading cycle under the whole curve. So they compare this area to this whole area. And they found also when they studied the energy dissipation that when the cyclic load increases, increases from time to time, the more the cyclic load increases after many cycles, the energy dissipation decreases. So we'll find that this loop decreases, and after an amount of cycles, the energy loop starts to be, or the amount of energy dissipation starts to become lower, as we can see in this curve. So this is the first cycle. If you compare it to the 10th cycle, we found that the difference in the loop is lower in the 10th cycle. And the more the cycles increase, like for example, if you run on a marathon or something, the more you exhibit cyclic loading on your Achilles tendon, for example, the more the energy dissipation decreases, which helps in storing the energy and decreases the amount of fatigue or increases the time that you reach fatigue after. Another study that they did to compare or to see the energy performance of the ligaments or tendons and to see the energy dissipation is compare between the maximum and minimum strain. If we look at this curve, we'll find after 2,000 seconds, the curve starts to asymptote. 2,000 seconds will mean about 30 minutes. So if a person is running a marathon after 30 minutes, this dissipation of the energy would be much less than the starting in the energy. The starting or the beginning of the running era. Now, one of the questions that kept me thinking about, and I kept thinking many times about it, how do they test it? How do they measure the stresses? How do they measure the strain and all these properties? How are they able to test it? So I was lying down in the grass and thinking about it, and then the idea came out. And I found this device on the internet, and this is how they do it. If we look at this device, we'll find that, of course, this is not a human leg. This is the femur, and this is the tibia of a rabbit. And they are using it to measure the stresses or the stress strain properties of the medial collateral ligament of the rabbit. They apply stresses, and then the way they measure the strain, they either use extensometers, or they can also use video cameras. Where the video cameras, they measure the strain, and they use an analysis to measure the strain that happened when they applied the stress. Another important factor is embolization on tendons and ligaments on their mechanical properties. Because when a person's hand breaks, for example, he has to put it in a cast. So his hands remains unmoved for a long time, which can affect on the strength of the muscles and also can affect on the mobility of the ligaments. So here I'm going to see the effect of the embolization on tendons and ligaments. The change in ligament generally occur more slowly than adaptation mode. This is basically due to that ligaments and tendons are less vascular than bones. The blood supply to them compared to bones is very minor. So that's why the changes in them is much slower than what happens in bone. A study that was done by Wu, what he did, he got some animals, I think that they were rabbits, and then he put the hands of the rabbits or the legs of the rabbits in casts, and he separated them to 4 groups. The first group was 9 weeks, the second group was 12 weeks, the third group was 9-week embolization, then 9 weeks active. The fourth group was 12 weeks embolization, then 9 weeks active. He found from this study that the rabbits that had 9 weeks embolization happened to decrease 69% in the ultimate load, and then 82% decrease in the energy to failure. However, for the 12 weeks, he found that 71% decrease in the ultimate load. And for the other 2 studies, when he did for the active rabbits, when he applied active, he found that as the rabbits started to get active after he removed the cast, he found that they started to gain their performance and the flexibility of the ligaments and the tendons fast after they did this experiment. As they increased in stiffness and strength, also came back to level of controls. We can see here the effects of strain curve for group 1 and group 2. If we look at this one, this is the control, or this is the normal case. This is the normal case, where we see on the y-axis